Okay, so good morning, everyone. For today's meeting, we will discuss the principles of mathematical induction. Now, to apply this particular concept, we do have three easy steps. But before that, let us define what is a PMI. So, a PMI is a mathematical proof or a mathematical proof method that is used to prove a given statement about any well organized set, especially sa natural numbers. Now, we have three easy steps. Number one is to show that P of n is true for n is equal to 1. Or basically, we will be showing that P of 1 is true. Now, for number two, or step number two, we will assume that the given statement P of n is also true for n is equal to k, where k is any positive integer. So all the variables n will be replaced by a variable k. Now, after that, we will now proceed to step number three, which is to prove that the result is also true for p of k plus 1 for any positive integer k. So, from a variable n to k plus 1. Now, the first step in here is what we call the base step. The second one is what we call the inductive step. Now, if the above mentioned condition is satisfied, then it can be concluded that P of n is true for all n natural number. Now, let's have an example. We will prove that the statement or the P of n 1 plus 3 plus 5, this should be there should be an ellipsis in here. Okay, for a while plus dot dot dot. These three dots are what we call ellipses. No, it's in here because there are terms in there, but we decided not to write it down kay taas naman kaayo. So that is 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. So we need to show that the left side of this statement is just equal to the right side. Now we will begin with step number one. We show that P of 1 is true. Okay. Now, your n will tell you what number you will be equating on the right side. Since we have used p of 1, that means we will be using the first term on the left side. Now, the first term in here is positive 1. So we just have to equate positive 1 to the right side of the statement, which is n squared. Now take note, our n in here, the value of our n is just 1 because this is originally from the form p of n. So we will replace n by 1 and we have to copy the exponent. We have here 1 is equal to 1 squared or 1 times 1, that is just 1. So we have successfully showed that p of 1 is true. Now question, ma'am, can we use P of 2, P of 3, P of 4, and so on? Yes, of course. So if you decided, if ever you will decide to use P of 2, let's say P of 2, okay, so we'll be using P of 2. That means the number that you will be equating to the right side of the equation are the first two terms on the left side, which is 1 and 3. So we have here 1 plus 3. 1 plus 3, that is 4. The value of our n, that is 2. So you square that one, you will have 4. The left side and the right side is equal. So we can use P of 4, P of 5, P of 6, P of 7. But take note, we have an infinite set of numbers. So it will take a lot of time for us to prove that the entire terms on the left side is equal to the right side. That's why we have the inductive step. So we will proceed to the inductive step. Now, in this case, we assume, just simply follow the step in here, assume that the given statement is true for n is equal to k. So we assume, okay, we assume that p of k holds where n is equal to k. Now, if n is equal to k, that means all the variable n in here will be changed into the variable k. This gives us, okay, that is, you write down, that is, we have here 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is just equal to k squared. So take note, we have copied the entire statement in here. The only thing that has changed is the variable n. Now it turned out to be a variable k. Now after that one, we show, you proceed to step number 3. Okay, we will show that p of k plus 1 also holds. So if we will assume that p of k plus 1 also holds, then this is what the statement looks like. We have 1 plus 3 plus 5 plus dot 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 plus 2k, right? 2k minus 1, and then we will add another term using the last term on the given statement sa left side. So from k in here, this will be replaced into k plus 1. Copy 2, right? Copy 2, k will be changed into k plus 1, and then we have copied negative 1. Now, on the right side, k will be replaced also by k plus 1. So we have k plus 1 squared. This means that at the end of our proof or at the end of our solution, this should be the phase or this should be the answer that we will come up with. Now, let's start doing this one. Let's start showing it. So we'll be using this. Take note that 1 plus 3 plus 5 plus dot 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 plus 2k plus 1 is just equal to k squared because we have assumed it, no? 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared. So we will no longer write down the left side of the statement. Instead, we will write down k squared plus we have in here the term that we have added, which is 2 times k plus 1 minus 1. Now let us simplify. We have k squared plus, distributing this, we have 2 times k, that is positive 2k, 2 times 1, that is positive 2, minus 1. So let us combine the like terms and simply copy those terms who do not have a similar term, just like k squared in here and positive 2k. Now 2 and 1 are both constant, so we can combine them. 2 minus 1, that is just equal to positive 1. Take note, our aim is to have k plus 1 at the end of our proof. So we need to factor this out. So if this is a trinomial, we can use the first term and the last term to factor this out. So the factor of k squared is just k and k because k times k, that is k squared. Now the operation in the middle is positive, so we'll be using positive in here. Now, the factor of 1 is just equal to 1 and 1 because we have here 1 times 1, that is just 1. Now, if you want to check if your factor is correct, you can apply the FOIL method. So we have k plus 1 times k plus 1. K times k, that is k squared. K times 1, that is positive k. 1 times k, that is positive k. 1 times 1, that is positive 1. Combining this two, this is 2k. We have k squared plus, and this is positive 1. So we still have the same trinomial. That means our factor is correct. Now we will go back to our very own aim to have this k plus 1 squared. So k plus 1 times k plus 1 is just equal to k plus 1 squared. We have successfully proved the given statement. Okay? Therefore, we will write down therefore p of k plus 1 also holds. Now, since we have successfully or we have satisfied the conditions above, we can say thus that P of n or this statement is true for all n greater than or equal to 1 by the principle of mathematical induction or by the PMI. So that is how you will use the PMI in proving some statement. Now let's have another example. Okay, we have in here, let's prove the statement. Let's prove the statement. Let's say 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 all over 2 for all n greater than or equal to 1. So we need to show that the left side is equal to the right side of the statement or the said equation. Now we will apply the PMI. So we have in here our proof. We start with the base step rather. So for the base step, we have in here, we show that P of 1 is true. So you can use P of 1 is true or P of 1 holds. That's up to you and how you will craft your sentence. So when P of 1 holds, we have P of 1 or the first term on the left side is 1. We will equate that on the right side, which is n times n plus 1 all over 2. Now, the value of our n in here is equal to 1, so we have 1 times 1 plus 1 all over 2. Copy on the left side, and we have here 1 plus 1, that is 2, times 1, that is 2. So we have 2 over 2, or 2 divided by 2, that is just equal to 1. Thus, P of 1 is true. Now we will then proceed to the inductive step. So in the inductive step, we assume that P of K is also true. Okay, P of K is also true. When P of K is also true, all the variables n will be replaced by K. So we need to indicate in here where n is equal to k. So we have 1 plus 2 plus 3 plus dot 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 plus k is equal to k times k plus 1 all over 2. Now we need to show, okay, for step number 3, I will be writing in here 3. We need to show, okay, we need to show that P of k plus 1 is also true. Okay? This means our statement in here 1 plus 2 plus 3 plus dot 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 plus k plus this term will become k plus 1. So we have in here k plus 1 is equal to the entire variable k in here on the right side will be changed into k plus 1. So from k, this is k plus 1. Then we have another k. Okay, that's k plus 1. Copy the positive 1 in here, and we have the denominator positive 2. This means that at the end of our proof, this will be the phase of our final answer or the final solution. Okay, now we will then start showing this one. I will be using the equal symbol. So we know that 1 plus 2 plus 3 plus dot 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 plus k is just equal to k times k plus 1 all over 2. So we no longer have to write the left side of the statement or the left side of the equation. We just have to write down k times k plus 1 all over 2, and copy the last term that we have added in here, which is k plus 1. Now let us distribute this one. K times k, that is k squared. K times positive 1, that is positive k. Copy the denominator, positive 2, plus we have in here k plus 1. Now take note, we will treat this one as a whole number. So when it is a whole number, the denominator will always be 1. We will get the least common denominator, or a number which is divisible by positive 2. I mean the smallest number which is divisible by positive 2 and positive 1. So that is positive 2 as well. The smallest number that can be divided by these two. 2 divided by 2. Okay, 2 is divisible by 2 and 2 is divisible by 1. So we have 2 divided by 2, that's 1, times the numerator, we have k squared plus k. Copy the operation addition, 2 divided by 2, that is 2, times the numerator, k plus 1. Okay, 1 times k squared, that is just k squared. 1 times k, that is just positive k, plus 2 times k, that is 2k, 2 times 1, that is positive 2, all over 2. So we will be combining the like terms. Here, we just have to copy k squared, positive k plus positive 2, that is positive 3k. We have in here positive 2 all over 2. Take note, our aim is this one. Now, we will factor this out. This is again, the numerator is trinomial. So we can use the first term and the last term to get the factor. Copy the denominator, which is 2. The factor of k squared is just k and k, because again, k times k, that is k squared. The operation that we will be using in here is positive, since the operation in the middle or in the second term is positive. Now we have in here the factor of 2 is just 1 and 2, because 1 times 2, that is positive 2. Now we can stop in here, but then again, our aim is this phase. So we will break it down. Oh, we already have k plus 1 for a while. We already have k plus 1, and then k plus 2 can be broken down into k plus 1 plus 1. Copy the denominator all over 2. So we have the same k plus 1, k plus 1 plus 1. K plus 1 is just the same with k plus 2. Now, we have successfully showed, okay, we will be using, let's say, therefore, for a while. Therefore, p of k plus 1 is also true. Okay, since we have successfully showed, or we have successfully satisfied the given condition, we can then say, thus, P of n is true for all right, for all n greater than or equal to 1 by the use of the principle of mathematical induction, or by PMI. So that is how you will apply the principle of mathematical condition in proving statements. All you have to do is to follow the 3 easy steps in here, or the 3 easy conditions. Now, if you do have questions, you may write it down below. Thank you so much.